In this introduction, I hope to give you a feel for what statistics is, what its role is, why it's useful, and hence why I think you should study it and not see it as a necessary burden to the main topics of your MSc. And lastly, I want to give you an overview of the statistical process. This is what you might call the bigger picture of statistics. And this can be used as a sort of map to see how the topics that we will cover in this course fit into the bigger picture of the statistical process of doing an actual research study. Let's first of all try to summarize the scope of statistics. So statistics is the science of learning from real data. It's about solving problems. And this is reflected in the historical development of the subject, which has been largely driven by a need for methods to help solve problems, from astronomy to gambling to medical sciences to social and economic sciences. And its attachment to real problems is what makes it so widely used and so useful, and also omnipresent in all facets of life. So a recent example is Cox proportional hazards regression model developed by David Cox in the 1970s, and that was developed to study cancer survival and the effect of treatment. And it's concerned with the collection, analysis and interpretation of data, as well as the effective communication and presentation of results that rely on data. So statistics is involved in almost all aspects of a research study, from the design through to the analysis, and also the way in which results from analysis are interpreted and how conclusions are drawn. Lastly, statistics also provides the framework of quantitative reasoning necessary for making advances. This is a more subtle point, but it highlights an important role that statistics plays in providing a framework for thinking. In particular for thinking clearly, logically and independently. It's not a toolbox of methods that need to be rote learned and blindly applied. Statistics as it relates to solving problems is about understanding and applying concepts. So in terms of science and medicine, it can develop our critical thinking skills, not in the sense of being critical for the sake of it, but in the sense of exercising good judgment, weighing up pros and cons and balancing evidence. For now, we can broadly define two types of statistics, descriptive and inferential. So descriptive statistics, this is concerned with summarizing and displaying the data that has been collected. So for example, if I were able to monitor whether students turned off this video, then I could describe the proportion of people who turned off before the end. There's no other interest here except for describing the sample. I might though then explore the data further and use some graphical or tabular presentation to show the distribution of when people turn the video off. Inferential statistics, on the other hand, go beyond the sample and try to estimate something about the population based on the data collected in the sample. So it might ask, for instance, are these data from this particular sample of students plausible with the hypothesis that at least 3/4 of all potential students who will take this course will watch this entire video? So the sample is the current batch of students and the population is all potential or future students. And the sample is just that, a sample. If I took another one, I would be likely to get a different result. It would vary, and we call this sampling variation or sampling error. So there's uncertainty in my sample. And inferential statistics quantify this uncertainty in a way that allows us to make inference from the sample to what the value might be in the underlying population. So in this example, to move from knowing the proportion of bored students in the sample to understanding something about the proportion of bored students in the population of all students who take this course. In a nutshell then, a large part of the role of statistics is to deal with unpredictable variation. A corollary is that if the study can be reproduced exactly, with no variation in results, then there is no need for statistics. However, I can't think of an example of an experiment that can be reproduced exactly. We just live in a stochastic world. Nonetheless, this role of statistics is such that some hold the view that statisticians are more interested in noise than in the signal. But this isn't quite right. A fairer assessment is that statisticians and statistics more generally is interested in the signal too, but recognise that noise or random error exists, and in order to draw valid conclusions we need to take account of this noise. This comes in the form of an assessment of the precision or the uncertainty that is attached to the signal. So here's an illustration of a very basic statistical analysis that shows that statistics is actually primarily interested in the signal too. So the interest here is in the association between body mass index, or BMI, and blood pressure. So blood pressure is on the vertical axis. So a statistical analysis tries to estimate this association or this signal, and the line in this figure actually shows a model for how blood pressure behaves with respect to BMI. So in the figure, the signal of interest is the slope of the line. The slope represents the association between body mass index and blood pressure. So it's a systematic component of the model that captures the relationship of interest. And the slope in this example takes the value of 0.9 millimeters of mercury. This value represents the average increase in blood pressure for a unit increase in body mass index. But we have to acknowledge that if we were to take another sample, we'd get a different value for our signal or for our slope. So there's a random component that comes in this study, and it's a random component of this signal here that we're trying to work out that will be affected by how many subjects that we have in the study, but also by the variation around this line, the randomness. So we try to estimate how much uncertainty there is due to this sampling variation or due to this noise. And we do that to get a confidence interval. A confidence interval gives us a range of plausible values for our signal, or for our association of interest, or our systematic component of our model. So here we get a confidence interval of 0.8 and 1.1. So you can see that the prime interest is in estimating the signal, but we also try to quantify the noise, so we get a sort of minimum estimate of uncertainty in the signal. And with that in mind, and this is a view that's widely held, one might think that if you've done a good experiment in the sense of having little random error, then there's no need for statistics. And it's true that a good experiment or study seeks to minimize this unwanted variation, but it's not always possible to reduce variation to an extent that statistics is not necessary. And that's just because, as I've said, that some things are just stochastic in nature. Consider measuring blood pressure, for instance. And not only that, we should really insert the word inferential in here, because as we've already mentioned, an important role of statistics is in the design of studies. And to do a good experiment, you need to design it well. So that involves statistics too. Knowledge of statistics helps you design good studies. So why learn about statistics? Well, statistics are everywhere. They're not just confined to medical and scientific research and practice, but they're in the news as well. So these are a random pick of headlines from the news on the day that I prepared this lecture. You can see a diverse range of topics from climate change to the Scottish referendum, and all of these stories are underpinned by some statistics. So understanding statistics is in some respect a life skill. It can help you to understand the world and consume the news that's around you. And ironically, one of the headlines using statistics was about poor numerical and statistical skills among graduates. In our information age, scientific and medical research is now widely reported in the media. And here's a random pick from the last few weeks, just in one newspaper. And that covered August, which is a quiet month. Unfortunately, these stories are not reported well. You can't get reliable information on a research or scientific or medical topic from a newspaper. The main focus for scientific reporting in the media is in generating internet clicks and readership. And so there's a lot of stories targeted at readers containing general health and lifestyle implications of research. We're given the latest bulletins in what we should be drinking and eating, how we should exercise and live our lives. We're even given information on whether we should keep the lights on or not before going to sleep. And it all comes from the latest research study, regardless of the quality. So it's difficult to sift through what's worthy of public consumption and what isn't. And almost always these reports, these newspaper reports, are written in fairly stark black and white terms, failing to recognise the uncertainty or the grey in research. And the Daily Mail, a newspaper in the UK with an average daily readership of almost 2 million, seems to be on a mission to classify every inanimate object into those that cause cancer and those that prevent it. Just look at the volume of inanimate objects they've written about here, collated free of charge as a service to public health by the owner of this website. And this is just for the ANs to the ASs. And for some of these inanimate objects, it keeps flipping from cause to prevention as new research materialises that contradicts the old. Now, journalists don't appraise these studies, and most probably don't even know what a systematic review is. That's something to look at the totality of the evidence. So that's the mass coverage. We also encounter risk directly to us. Whether you're in the position of a doctor or a patient, we live in a risk-centric society. And much of the information we receive is in the form of a risk or a probability. Consider screening programs, for example, cervical and prostate cancer screening, results of blood tests and treatment pathways, fertility tests, a relative deciding on whether to have joint surgery done. It can be tricky to make sense of what all these risks mean and use them in a way to help us make decisions. And you'll see on the course how the presentation of risk can mislead. So whether or not you agree with the quote by H.G. Wells, that statistical thinking will one day be as necessary for efficient citizenship as the ability to read or write, it's fairly clear that statistics touches on so many areas of our lives. Understanding what's behind such a volume of statistical information may thus be a useful life skill, not just for you, but also for you to communicate to others. And some efforts are being made to work out ways of communicating risk to the public in a more palatable manner. There are some examples on this website. Another reason to learn statistics is so that you can read and appraise research independently. You can't rely on peer review as a quality standard. Research is not good just because it's been published. The process of peer review is good, but it's far from faultless. For example, Fiona Godley in 1998 manipulated a research paper to include 8 methodological mistakes. This paper was then sent out to over 200 reviewers for comment. The average number of weaknesses picked up on was only 2, so you can't rely on others to have done the quality control on your behalf. In systematic reviews, a process of consolidating the available evidence from a large number of studies that address the same question, the reviewer often concludes that the methodology and scientific evidence from available research is of poor quality. And even prestigious journals are not immune from basic mistakes. For example, a study of papers in 2001 showed that 38% of articles published in Nature and 25% in the British Medical Journal reported test statistics and p-values that did not correspond to each other. In this case, the mistake could be trivial and unlikely to affect the general conclusions. But we do not know. It's more the frequency of the mistake that is so surprising. And most published research findings, or so-called discoveries, are actually false, and this was explained and supported through theoretical arguments in this paper here, and it's one of the most highly cited papers in recent years. In nutritional epidemiology, there are many examples of findings that failed the test of time or failed to replicate in subsequent studies, in particular studies on the health effects of micronutrients. Here, there's a pattern of observational studies finding beneficial effects that are subsequently refuted by randomized controlled trials. For example, look at the literature on the effect of vitamin C and E on cardiovascular disease. And something called confounding is thought to explain most of the observational results in this case. Folk with healthier diets or who take vitamin supplements are more likely to be healthier in numerous other ways that lower their risk of CVD. And it's impossible to control for all these factors in an observational study. There are also many other reasons why findings tend not to replicate. For example, there's publication bias towards reporting positive findings or results that show something, show an effect. They're generally perceived by researchers and journal editors as more attractive. And there's also financial interest as well, for example, grant funding and commercial interest in research that shows an effect. And the wide range of research designs that's available also open up the potential for false positives, as they provide a multitude of different ways in which bias can affect a result. And researchers and academics like to tell a story too. They like a narrative. This paper here shows evidence of selective citations by research papers to support their general results or to support their general theory or viewpoint. And you can find almost any study that will support your view. So the point is that often research findings are wrong. There are biases, selective reporting, etc., etc. You can't rely on publications to do the thinking for you. A degree of independence is required to navigate and make informed judgment around research. And that independence of appraisal comes through understanding statistics and research methodology. So learning statistics can enable you to become an informed consumer and thinker of research. And of course, understanding research enables you to conduct research better, to conduct effective research. As well as the obvious point here concerning conducting analysis, understanding statistical concepts and the principles of research methods encourages the design of experiments and studies that allow conclusions to be drawn. There are too many studies that are just inconclusive due to poor study design. In certain studies involving humans, this can actually be unethical. Think about the ethics of asking a person to participate in a study which is ultimately futile, that won't contain enough information to answer the question, or will be set up in a way that does not give a valid answer to the question. It's like asking a person to give blood and then throwing it away. Statistics is by nature analytical. It tries to reduce a problem or theory to something that's testable and provides ways of testing it. As mentioned, its applications are concerned entirely with trying to understand something. The concepts of statistics provide a framework for thinking about problems that are stochastic or contain randomness, and also for thinking about causality, and these are useful transferable skills. So statistics is useful, but it's not intuitive, so it does need to be studied. As humans, we're very good at spotting patterns to help us make sense of the world, but as a result, we often see patterns when none exist. Or put another way, we're not very good at differentiating background noise from a true signal. Look at these two boxes containing a sequence of 100 zeros and ones and decide which one was generated randomly by flipping a coin and which one was generated by someone trying to mimic a random sequence. So the true random pattern is actually the one on the left. Now most people would choose the one on the right because the one on the left has a more streaky pattern or longer sequences of zeros and ones. sequences that we'd probably associate with something not random. An analogy here is the so-called winning streak that we observe in sport. So for example, you may see your favourite player go 5, 6 or 7 games without scoring a goal and infer a drop in form, or see them score 6 or 7 games in a row and expect their transfer price to rise, when actually what underlies the sequence is just randomness. The figure also highlights that surprising things, or what we call coincidences, are not as uncommon as we perceive. Even in the sequence of 100 coin flips, we had a sequence of 8 zeros and 7 zeros in a row. Most of the things that happen in life that we perceive as coincidence should not actually surprise us. It's just that we process them incorrectly. Here's an example. In 1981, the 4-digit lottery number 8092 was drawn in both Massachusetts and New Hampshire. It was reported as a 1 in 100 million event, a massive coincidence. However, it should have really been described as a 1 in 10,000 event, as we'd be equally surprised if any pairs of the possible 4-digit numbers had been picked. Further, if you include the fact that this lottery had been running every day for about 3 years, and also the number of possible pairs of states that could be compared, the result is even less surprising. So if our ability to quantify randomness or uncertainty using our intuition is not so good, then we need methods to help correct us and stop us making fools of ourselves. Another reason why we need statistics. There are many examples of fallacious statistical reasoning. This one is the case of a famous actor and ex-American footballer O.J. Simpson, who was accused of killing his wife. There was evidence of domestic violence towards his deceased wife, but the defence told the jury that of the 4 million women battered by their husbands the previous year, only 1 in 2,500 was actually murdered. That sounds like a compelling probability for the defence. But the more relevant probability is this one. Of all the women who were subject to physical violence by their husbands that year, and also murdered, 90% were in fact murdered by their abusive husbands. This is what's called the defence attorney's fallacy. And similar errors of reasoning occur when interpreting test results from medical screening. Once you start to understand the concepts of statistics, you see its fallacious use in many places. Here's an innocuous example. Mark Lawrenson, or Lawro, is a BBC football pundit. Every week he predicts the football scores, and each week a different celebrity has the chance to go head to head with him, but they only get one go. The league table is based on the one-off scores for each celebrity and the average for Lawrenson the football pundit. Now, predicting scores is a random process. Some weeks Lawro does well, and some weeks he does not so well, as shown in his best and worst scores. However, his good and bad scores get averaged out in the league table, while the celebrities' good and bad scores don't. It's no surprise then to see a few of the non-football experts who get lucky on a one-off occasion above Lawrenson in the league table. In fact, any extreme measure taken from a variable subject to randomness is more likely to be closer to the average if measured again. And that's just because more extreme values are less likely to occur, whereas more likely values, such as those close to the average, are more likely to occur or are more probable. This is called regression to the mean. So this isn't a fair table for Lawro. He doesn't stand a chance. And regression to the mean is a common flaw when interpreting results from medical studies that involve change or that look at change. For example, say you took the blood pressure of a group of patients. If you were to repeat the measurements the next day and then split them into 2 groups, those in the top half of the BP distribution and those in the bottom on the first day, the group in the top half will show an average decrease in blood pressure, and the group in the bottom an average increase. But nothing has happened. It's just that any measure that involves a degree of randomness will tend to be closer to the average following an extreme observation. It just reflects a smaller likelihood of obtaining an extreme value. And regression to the mean also explains why a sequel to your favourite film or your band's second album is often disappointing. Interpreting statistical analysis often involves flipping the way we naturally think. Often in life we observe samples of things, then make generalizations about the true underlying behaviour. It's an inductive process, an inductive thought process. For example, I go on holiday to a particular place and it rains every day. I then draw the conclusion that the weather is probably better at home. So I'm moving from data, the weather, to theory, whether it's better than at home. In statistics, in particular the type of statistics we cover, which is called frequentist, we often have to flip this around when we interpret results. So we start off with the condition or assumption that there is no difference in weather, that's the theory, and then look at the probability of samples under this assumption, that's the data. The key idea is that the data are the random part and the hypothesis is fixed. The weather is either better or it isn't at home. It's not probably better or probably worse. So the weather I experienced while on holiday behaves randomly because it was just a sample. So we look at the probability of getting that sample if there is no difference in the weather at home or on holiday. We then use that probability to make an inference on whether the weather is better or not at home. And what I've just described is the logic behind a p-value from a hypothesis test, and we just don't naturally think in this way. Statistics and this way of thinking is also entirely complementary to the scientific method. The aim of science is to understand nature. A theory tries to explain nature and is expressed as a testable model. Nature is then captured through experimental observation and quantified with data. And this data is then used to test whether the theory or the model is wrong. We can never prove that a scientific theory or a model is correct, just like we can a mathematical theorem, but we can falsify it. Falsification was proposed by the philosopher Karl Popper as a philosophical principle for how science progresses and what demarcates science from non-science. In a nutshell, what separates science from non-science is that science has testable theories. These theories can never be proven, and that's a logical statement, but they can be refuted or falsified. Popper's view of science is now widely accepted, and it is complemented by the nature of statistical inference too. Statistics never proves a model, it only measures how consistent the data are or are not with a model or a hypothesis, and that consistency is measured in the form of a probability. Statistics and research methods play a role in all aspects of the scientific method except for the development of the theory. Statistical thinking can be useful to help reduce or simplify a theory to a testable model or a testable hypothesis. We might broadly state this as defining the research question. A role of statistics that's under-recognised but is perhaps the most important is that of designing studies and experiments, and this has to be done in a way that tries to maximise the validity of the inference that's made from the data to the model. For example, minimising potential biases and controlling for unwanted variation in experiments or observational studies. And lastly, possibly the most recognised role of statistics is statistical inference, the aspect that allows us to make inference from the data to the model. Lastly, let's give an overview of the statistical process. Some might call this the bigger picture of statistics. The idea is to summarise the statistical process of a study so that you can see how the different elements of this course fit into this bigger picture. So it's a bit like a map that you can use to orientate your learning to. So in principle, we begin a study with a research question. And statistical thinking can help us define this question here. Falling out of that, we then identify the group that we wish to study, and we call this a target population. So a population statistics can be a population in a literal sense or something a little bit abstract. For example, it might be the underlying behaviour of something in a molecular experiment, or even a notional population, for example in the trial of a drug or future disease patients who will be treated with this drug. In most cases, the entire population cannot be measured, so we take a sample from this target population. And we use principles of study design to help us collect these data. Once we have the data, we need to organise, explore and present it. Typically this is used to check data, understand the sample and validate the data collection process. For example, in a randomised controlled trial, did the randomisation work? Are my two groups similar in characteristics? And we also use this exploration of the sample data to check assumptions on which statistical inference will be made. Sometimes descriptive analysis is an end in itself, for example a pilot study. We then use our tools of statistical inference. These might include estimating the true value of something with a confidence interval. For example, estimating the mean effect of a new drug over a standard treatment. Or perhaps performing a hypothesis test to answer whether the difference we observed in our study could just be due to chance rather than a true effect of the treatment. And also perhaps for prediction, what is the normal reference range for a biochemical marker in a blood test? Or can we predict whether someone has a disease based on a screening test? Most of this course focuses on estimation and confidence intervals. And understanding statistical concepts helps with the most important part of the process, and that's interpreting results and drawing conclusions. The first and biggest part of this course are the foundation topics. It's also the most important theme in the course as it tries to embed the main statistical concepts. And you'll notice that the topics don't occur in a linear fashion around this map, but that just reflects the fact that statistical ideas and concepts are interlinked. Also, I think it's useful to start off broad, covering lots of the bigger ideas before delving into the topics a bit deeper. This is what the first theme, called Foundations, aims to do. It covers topics 2, 3, 4 and 5. 5 deals only briefly with probability. Probability is a theoretical foundation that underpins statistical inference, but it also hovers in the background of the principles of design too. It's not necessary to understand probability to understand the core statistical concepts, but a little understanding may help you think deeper about the other topics, so we touched on it very lightly in the foundations theme. And the other topics can then be fitted in around this map. So you might find it useful to think about these topics when you come across them in the context of this bigger picture. And just to summarise what we've discussed.